center in France. That would be like, say, the symbolic structure would be like Eiffel Tower. So then you had to have like a large deformation, and then there was plasticity and also heat. This because the pattern of the failure here was really that you had like a fire that really weakened the yield stress of the particular steel columns here, and then after that, of course, it was easier for it to collapse. So we were studying the eventual instability problem when you have a large deformation, elastoplasticity plus heat transfer. This was done by a very good student of mine from Vietnam, Van Minh Ngo, who's now professor at UTC, Hanoi, UTC, University of Transportation Communication, Hanoi, one of the best places there. So basically, what was the idea? Well, we had to find a simultaneous load case where you have like an impact, which we simulated by imposed displacement. And on top of that, you had like a temperature which is weakening this structure at the same time. So these are truss bar in large deformation. I have studied these in a very detailed way. So I showed you what to do this when you have a large deformation. Obviously, if you really want to understand how to do plasticity, this is this one-dimensional case that I actually presented here. So basically, let me go and illustrate it again. This is basically the stretch is split into multiplicative elastic and plastic stretch. And if you take a logarithmic strain measure, that becomes the plastic strain plus elastic strain additively decomposed. So it becomes really like a standard way you compute plasticity plus the standard way you take into account large deformation. So it becomes just superposition of two nonlinearities. This is really the biggest merit of this approach because it kind of splits the geometrically nonlinear and material nonlinear problem. And you really can build your formulation in a very nice and let's say modular way in this manner. So going back to this work, what we have done after that is basically carried out this simulation. First of all, when you have a thermomechanical coupling, of course, you need more of these data. So we chose something that is typical of steel. That's C2, 10 to the power 5. Yield stress is 250, so it may be a little bit smaller quality of steel. With the ultimate stress being 300, then plastic hardening modulus is roughly 10% of this guy. And then softening moduli and so on and so forth are produced in order to be able to carry out this computation. We were able to show that we know how to handle localization. This is something that I mentioned when we discussed this in small deformation setting. The same thing goes into large deformation setting. You have to have this enhancement of the displacement field to handle the corresponding, let's say, localized failure and so on and so forth. Now, if you have temperature, of course, the material properties like yield stress and all the other properties depend on temperature, and we have chosen that as the temperature increases, those values go down. So what is the consequence of this choice? You can see here, if you have temperature independent properties, you can push this steel bar into very large deformation. And you recall, whatever is the dissipation, it's the area underneath this curve. Then you bring it to the first field, then you bring it to the ultimate saturation stress, and then you go down to something. So without temperature dependence, there is a sizable contribution of the plastic dissipation. With the temperature dependence, you go down. Basically, what Van Minh Ngo, he already had some experience before coming to do thesis with me at the Economa Superior de Cachan. He already did some kind of design, and right now he has also a company on the side trying to do lots of design. For some strange reason, I never understood. In Vietnam, they use Eurocodes. So what he was taking is like a definition of how these material properties change according to Eurocode. So it was not a simple linear degradation of the elastic strain like we were doing here. You see here, we did everything was like just going back to this one. We took all this to be linearly reduced. That means when temperature goes above the reference value, you reduce the yield stress and you reduce saturation stress, and everything was done linearly. What we are doing here, we were doing a little bit more realistic, whatever that more realistic means, because it's set in the Eurocodes, and I don't know who developed this, but anyway, we trusted Eurocodes, because then it was just illustrated approach. It was not really done for any client who was paying a lot of money. So the idea is like there's really much bigger reduction with respect to very high temperature. You can see when temperature goes down to up basically to whatever 600, 800, and there's really sizable reduction of these. And so you can see that as the consequence, the steel, which is very ductile material under room temperature, let's say 20 degrees or 30 degrees, when you go to very high temperature, really ductility is completely lost. And that is the reason, the explanation why this World Trade Center went down, because you lost all the ductility, which is typical of steel. And then basically the failure came in a very quick manner. So basically, here's of course, this simultaneous computation with the thermomechanical loading, and you can see that you can break the structure faster if you attack both with thermomechanical loading as opposed to only mechanical. It's really strange. This curve is red, this curve is blue, but in the legend, this one is green. I don't know how this color changed, but that's the way it works. The mystery of physics multimedia presentations. So after this was the end of this large information. In fact, I wanted to discuss a little bit like thermomechanical coupling, which is basically chapter 7, and also relies on chapter 6, which is time mitigation schemes. What happened when you have something more like a brittle failure case? So what is the problem of this study? We were hired at a certain point. There was a thesis of one of my good French students who was a product of Economia Supérieure de Cachan, Jean-Baptiste Collier, who is now a professor at the University of Lille. So we were hired by CTTB. This is Centre Technique de Tuiles et Briques. This is the technical center which helps all the industry partners in dealing with masonry products. And basically they had a desire to bring some kind of a modeling enhancement of in understanding of the modular tests that are built to certify the fire resistance of any new brick product. So basically this is the way it works. First of all, this is a typical brick that is used in France. This is 50 centimeters long, 20 centimeters wide, and 20 meters high. And you simply put a brick wall by putting these bricks, and of course a mortar joint in between. And inside these bricks, you have many of these so-called alveoles. These are empty spaces which are supposed to bring let's say, a thermal type of quality to this type of structures. Anyway, all those who live in the brick type of structures, they know that thermally they are certainly much better than many other types of structures. So the only thing that we are concerned about is what happens when you start the fire. And typically, CTTB, this Centre Technique de Tuiles et Briques, was certifying this fire resistance by taking into account things like what you call it modular tests, where you you build a brick wall. Here is one of these walls, and then you start the fire on one side. You start to control the temperature during a certain level, and then a certain duration. In particular, the duration was 6 hours. So this is considered to be long enough to make sure that such a brick wall, let's say, would stand until the fire brigade would intervene. So even in the busiest cities, what is kind of estimated to be a reasonable time is 6 hours. So if you start the fire and the firefighters come within 6 hours and try to put it down, then you are safe. Normally, that would be the idea. Now, so what the testing should show, what the testing should demonstrate, what it should show, basically that when you have a temperature that is kept constant for 6 hours, that the wall would not collapse. Now, if it collapses faster than 6 hours, obviously this is not good. This is not good design. It cannot be used to guarantee the fire resistance of such a structure. And if it does not collapse in 6 hours, but it takes much longer, again, it's not good because it's not economical. It's probably too strong for fire resistance. So you want to kind of first understand, to bring any new product within this 6 hour type of span, you want to say, to do this modeling and then do that. So please note that we have to deal now with the thermomechanical coupling, with the basically failure criteria for such a material. Now, this is what you call a clay material, what is called a dry clay, which was produced by in furnaces by what you call it at certain temperatures. See what kind of temperatures there, and then you mold it into this particular brick. And so you have to understand what would be the kind of typical damage mechanisms which might be produced under thermomechanical coupling, such as there's also a complexity that geometric arrangement for such a structure is very complex. It's not simply a 3D solid material, but rather it's like lots of these parois, what you call separation type of layers that are built together in the horizontal way and the transverse way. Typically, those that go into the longitudinal way, they are stronger than those going into the transverse way. So there's lots of anisotropy, at least orthotropy. There's one behavior in the direction of the wall, and there's one behavior perpendicular to the wall. Plus, another type of non-homogeneity is brought by these alveoles, these empty holes which are used for thermal. and you have to handle this. You see the way we handle this in terms of heat transfer. Because although this is not part of mechanics material, still there's something called radiation heat that takes place into these holes, and that has to be taken into account. So how did we approach this problem? We put it into sort of multi-scale environment. In other words, there is a structure scale, which is the scale of the whole wall. Let's say something 2 meters high or 2 meters wide or whatever it is, with maybe 2.5 meters high, something which is representative of the real wall in the real life building. Then we have the mesoscale. This is a particular masonry block. As I said, this is the one 50 times 20 times 50. And then we finally had the fine scale, which is a sort of material scale, which is a piece of this clay used to build such a masonry structure. So, in fact, the damage mechanisms were then worked out at this level of the material scale. And then you go through computation to bring what that means for the structural scale. So the way it worked is the following. First of all, you had a particular structure of this block, and it turns out that this block, when you look how it is working, is a part of the wall. So the wall is exposed to fire. Down in the basement, it is built in. It cannot deform. But the fire on one side makes the temperature gradient goes in horizontal and vertical direction. So the wall will bend both in the horizontal and vertical direction because of the temperature that is heated on one side and not on the other side. So basically, this way, you have to be able to couple the membrane action in these transfers, let's say separations in the block, and the bending action in these longitudinal separations between different holes in the block. So this was done by using a flat shell element. This was a paper that I wrote a long time ago when I was after my thesis doing postdoc with my advisors, Bob Taylor, Deb Wilson. I think among the papers, this is probably one of the most highly cited papers. This is a paper which is now producing so-called a flat shell element with 6 degrees of freedom as the combination of the blade bending element, in particular the steel Tyrkov blade bending, and the membrane element with rotation degrees of freedom. So every degree of freedom has 6 components that, every node has 6 degrees of freedom, 3 displacements, and 3 rotations. So it's very easy to couple, to build something around this wall that you split in the cell. So this would be like a plate action between the membrane action, and given that these membranes, they have rotation, you can very easily couple them together. Then inside these 4 plates or shell elements, flat shell elements that are coupled together, you stick in one of these heat radiation elements, which is supposed to simulate what happens in transferring temperature through the empty space. Basically, you have this solution to the heat radiation problem. So the domain becomes rather heterogeneous. You have the membrane, the bending action represented by the shell element, and you have a heat transfer type of action represented by the, let's say, solid heat transfer type of elements, and coupling all together into thermomechanical coupling. So all kind of interpolation have to be defined, namely for a displacement field and rotation field. Of course, you have to devise the corresponding interpolation for these shells in terms of displacement and rotation. There's also, this is like plate bending rotation. This is a drilling rotation, which is perpendicular to the plate of this shell. So basically, this has to be developed with very carefully, because you have all kind of locking phenomena in plates and shells. I didn't talk about that. This is another course, really the full thing to talk about structures, what you have to do. And basically, the idea is like you need incompatible modes and all kind of stuff to handle this. In any case, what you want to be able to provide is the typical damage pattern of such a wall. So in order to do that, we go to this material scale. In other words, we check one particular shell element and see what could be the damages inside such an element. And so basically, the idea goes as follows. We have built elastoplasticity, and these are small strain because these are cohesive materials, so there's nothing to worry about here. For large strains, so I go back to small strain, and we got this plasticity we talked about in more detail, so it will be certainly easier for you to understand. So the ingredients that have to be defined is the total strain being elastic plus plastic strain. Then the free energy is the part of the elastic energy, total strain minus plastic strain times the elastic, let's say elasticity tensor times the strain total minus elastic. And then there's this hardening or rather softening phenomenon that takes place when you start breaking the wall. Related to this type of strain energy, of course, you have a yield criteria, which I'll define in a moment. It's always pictured here. And then once I have this yield criteria, I'm just trying to find my corresponding plastic strain and my softening variable. So what we have chosen here is this Sangana plasticity criteria, because these are cohesive materials, and they are really very sensitive to mode 1. So mode 1 is really, the way it's presented is if the elastic strain, the principal value, reaches the corresponding yield strain, you basically break the wall. And then you turn this elastic strain into the stress by multiplying with the corresponding mechanical properties. The K is bulk modulus, G is the shear modulus, and you provide the yield surface in the standard format. In particular, you have here two yield surfaces. You have for the first principal strain, and then you have for the second. But please note, the first principal strain should always be equal or bigger than the second. So in fact, the real active yield stress is this for the first strain, and then the second one reduces only to a point. So this way, from the strain field, I can put into the stress field. I think I already displayed that in the moment. And then you can put it in terms of the stress resultant. So from a full surface plasticity criteria at the level of the strain, that is, you have a first principal strain, a second principal strain for every layer of the shell. You now turn this into stresses, and finally you turn it into stress resultants. Namely, stress resultants are computed under the hypothesis that the stresses are uniformly distributed for the membrane stress. For the membrane forces, these are N alpha beta, alpha and beta being 1 and 2 in direction 1, 1, 1, 2, and 2, 2. So these are like two membrane forces and two membrane shears. And then for the bending part, we took a linear distribution, and as soon as the maximum stress or minimum stress reaches the value of the yield stress, we then assume that this is a breaking. This way, we don't take into account some kind of distribution, but even these are very brittle structures, and basically it's not much of an approximation. So from the strain, I can do the stress, and from the stress, I replace this with the stress resultant. So at the end, I recover from these two surface plasticity in the principal strain case. I recover four surface for the membrane bending, and so on and so forth. So that becomes a full surface plasticity computation that I could do. Now, the typical behavior of these materials is in compression and tension is pictured here. So basically, you have a certain amount of energy if you break it in tension. Typically, you only have one crack, and the energy is rather small. It's called GP. This is the fraction energy in tension. Or if you build it in compression, when you squish the wall, you have a bigger amount of energy, which is called GC. This is fraction energy in compression. So if the wall is breaking, or rather piece of this material is breaking in compression, it's not going to be breaking in tension, and vice versa. So we can afford to put the softening variable, which is saying how much is the yield stress reduced with the failure process, into a single, let's say, internal variable, and you can just switch from the compression to tension by using this smooth transition to taking a function tangent hyperbolic related to the principal value of the elastic strain. So if they are dominantly tension, you're going to use something which is a tension fraction energy, which is here, or if they are predominantly compression, you're going to use compression fraction energy, which is given here. And this is basically how we build the mechanical model. Now, what is the dependence of this model on temperature? Well, basically that all these properties are dependent on temperature. That is yield stress, hardening variable, and so on and so forth. In fact, for this particular model, this is, as I said, the clay material, which is baked, if I could say, at certain temperature, something like 800 degrees. And you can see that contrary to steel, but the yield stress goes down when the temperatures are increased. Here, actually, the yield stress goes up because you go recover this kind of internal structure of the material when you kind of in the temperature where you're making it. And then at a certain point, when you reach beyond this temperature, then again it goes down. So it's very complicated dependence on how the yield stress and the other mechanical material properties depend on temperature. What is dependence on the, let's say, temperature mechanics? Well, first of all, you could add this the plastic dissipation to be an additional source of heating, but in reality these are very brittle materials, so the source of the heating is not that big. You can even neglect that without any major problem. What is really needed to take into account is basically the fact that the heat is propagating not only through these parwa, what you say, the layers of the brick, but it is also propagated through these holes. So recall, on one side you put lots of very high temperature because of the fire. On the other side you have ambient temperature, whatever, plus 20 or something like that. On a day like this, plus 7, 8 outside. So basically the idea is that you have to capture this propagation of heat flux from heated side exposed to fire to the side which is exposed to ambient temperature. And in this propagation, goes to these alveoli, these empty spaces that are sitting inside the brick. So for this one, you need computation of radiative exchange that is typical. Basically, it's also like a sun sending the heat to Earth and stuff like that. These are the kind of computation we're talking about. And it's known that this is proportional to the temperature to the power of 4. So you need to have exchange, equilibrating, if I could say, these fluxes over the 4 facets of the hole. Now, when the brick starts damaging, you'll see that in a moment. Basically, what happens, you have a one by one, these layers are breaking, and so the hole, which was only one, is because of the layer that in between broke, it becomes 2 holes, 3 holes, and so on. So basically, what the mechanics is doing to temperature during in the course of damage is basically removing these walls so that you have to do now radiative, let's say, equilibrium type of exchange over the 2 holes and so on and so forth. So this is how we go forward. Now, in terms of the time integration schemes, we discussed different time integration schemes. This is a perfect illustration. You had the one for the heat transfer, where you started yesterday with this time integration scheme for the, let's say, this non-stationary heat transfer, and I explained how you can do that. You need so-called alpha scheme. It could be either implicit or backward, or it could be explicit or forward, or it could be trapezoidal rule. So you can see the typical approximation for the, let's say, the heat transfer problem, which is here. So you have this capacity matrix times the nodal area temperature. It's approximated with a, let's say, derivative here, and then you have this contribution from the in the heat flux. It could be nonlinear function of all of these, including the plastic deformation and so on. If you're going to take into account all these plastic dissipation and stuff like that, so that means you need plastic deformation and hardening and so on and so forth. Now, on top of that, here you have equilibrium equation, and again, temperature dependence comes in from the temperature dependence of the properties. So on top of these global equations that concern all the nodal values of displacement and nodal values of temperature, so for the shells like that, you have 6 degrees of freedom, free displacement, free rotation for every node, plus the 7 degree of freedom is the temperature. And so basically, you have to compute this kind of, for every node would be 7 degrees of freedom. And for every Gauss point of such a shell element, you also have to compute how the inelastic deformation is evolving, that means plastic deformation and then bending and something like that. Now, the key difficulty is the following. On one side, let me go back to this picture. On one side, you have something which is supposed to last for 6 hours. That is the temperature program where you heat it with the fire and then let the fire last for 6 hours. And if you have a damage, the damage is basically a fraction of a second. So you have a time scale of evolving the temperature, which is very large compared to the evolution of this plastic strain and the damage variable that are representing the failures. So basically, if you start computing this in time, using the 10 time step, of course, what you're doing is really something which is not very meaningful. So if you really want to last for 6 hours in terms of computation, I mean, if you take a fraction of a second, you're going to have many steps. And you could see that many of these time integration schemes will be in big trouble by doing so. So basically, we better change this type of idea. So the way we did it is we said, okay, if the temperature is supposed to be evolving over 6 hours, then we can take a time step for the temperature evolution to be very large, of the order of minutes. And that means that inside the particular time step that is evolving the temperature for a number of hours, that can happen many of these damage events that we are controlling at the Gauss points. So symbolically, this is written like you have a one big step for temperature, and inside this step you can have many small steps of the mechanics. In other words, you don't solve this simultaneously, mechanic and heat transfer together, but you solve, let's say, a big step of temperature, and inside you solve many of these small steps for mechanics. How many small steps for mechanics? Well, depends on how much damage you have. What we've done, we have chosen the criteria that inside the particular mechanic step, the kind of damage that is quantified by this softening variable should be, let's say, limited. That means you take a target value that you want to have maximum producing this damage. And with this one, you can decide what will be the time step that we are running. And then basically, we fill in the time increment for the temperature with a number of these events or failure of these particular, let's say, Gauss points. And then at the end we synchronize. If you go over certain value, which is the chosen value of the time step for the temperature, then you go back to reduce this one, the last one, so that you have synchronization between the value at the end for temperature, the value at plus one for the temperature. So basically, you have a like really very large temperature time step and smaller mechanic step, so you can run it. And this actually what is giving us all these really good results. And also, do I have it here? Yes. If you can also do it now with the different time steps, you can really have like a big speed up of the computation. Basically, having this, you can cut the computation time in half. And basically, this is like a one big thermal step with also small mechanical step, and this allows you in the ratio of these two being very large to cut computational cost in half. What have we managed to achieve? What we've done is basically we could not show in our papers, we could not show the real thing because this was proprietary. The CPTB was paying for this work, so we could not really deliver what we did for them. We delivered only for those guys because they were paying, but for our professional duties like being researcher and university professors and whatever doctoral students, we did publish some papers. So in those papers, we presented like simplified model. What is a simplified model? The wall is deforming in a very strange way. In other words, you have this because of the fire. You have a let's say curving of the wall around the horizontal and also in the vertical direction, and the one at the bottom is fixed. So basically, with this type of thing, you have like really deformation, which is three-dimensional. Yet we say, okay, forget about three-dimensionality. We're going to turn it into periodicity. So a particular brick is supposed to be periodic. So we just took a single brick, taken out with the periodic boundary condition to be inside the wall. So we modeled this brick with what is shown here with the 3 layers of these shell elements. So around every of these alveoli, these holes which is doing heat radiation type of thing, we put a particular shell element. So altogether we had 270 radiation elements in 3 layers of this. We had 597 shell elements, and then in between the shell elements and this masonry type of structure, the clay material, you have to have like a mortar. So basically, this mortar thing is basically the stuff that is needed to get a really good match when you have an initial type of development of temperature. Otherwise, if you don't put the mortar, it doesn't really fit in that part there. So this is the kind of stuff that we managed to do. Since we have a shell element, we can monitor the temperature on the upper and lower surface of every shell, and you can see that this time evolution of temperature fits very well the one which was measured experimentally. So you can see that the upper and lower surface is really fitting between what was measured inside this brick walls as we go along in time. You can see also that we can get very good distribution of temperature. So from the heated space where you have a fire all the way to the space which is close to ambient temperature, you have this distribution of temperature at a certain point in time. Now, what happens in terms of damage? We could see the damage variable, that means the self-softening variable side. You get some sizable values at the space which is exposed to fire, and that really corresponds to typical damage pattern. You can see the wall, the way it was built, and the way it was damaged by fire. So you can see it's just peeling off layer by layer the way it's exposed to fire, and you kind of destroy the wall in this way. So we are able to capture all these results in a very meaningful way. So these guys at CPTB were very happy. The only problem is after that, the guy who was working for that, he was supposed to be working for CPTB. Then he found a job as a professor at the University of Lille, and that all went to what can it do? They just got the code, but I'm not sure they know how to use it. In any case, they luckily they paid for that, and my former student is now a professor, so probably he's happy, everybody's happy. Maybe CPTB is not happy, but if they need the job again, you do it again for the better way with the tools that we have nowadays. So basically, the idea is really that we were able to obtain a very remarkable result. If you think about the masonry structures, I mean, those who ever look into the application like earthquake in masonry structure, this is typical of many people working in Italy, because Italy had a huge heritage from times of Roman Empire, where many things that were built in brick structures and they are still around. And even these older structures that are built for, let's say, people living in these different cities in Italy. And every once in a while, quite often, in fact, there's earthquake in Italy, and then there's a heavy damage of these masonry structures. But if you look how they do this work, it's really like a very simplified type of setting. So if you really want to do the same thing in this type of modeling, I mean, it's a really kind of a stuff that you cannot so easily do. Let me see if I have something that is still here. Yes, it must be this one. Let me just see if I got something. You know, basically, this masonry structures in Italy, they have very simplified modeling. So for the fire resistance, you already had this result that I showed you, which is a very sophisticated result, which needed a whole lot of things to be understood this properly. But I wonder if I have it here. Just a second, bear with me, please. Like this, maybe I this it here. Wanted to show you another one. This is waiting on presentation. This one. There is this one. And, that's not it. Let's see that. So imagine if you had a imagine if you had a structure like this. So do you see this movie? Hopefully, huh? So this is a typical test on a shaking table on masonry structure in earthquake. So you can say that this structure survived, but in reality, you know, you would not want to live in the building like this, definitely. So basically, if you really want to run this in a meaningful way, and you want to be able to estimate the damage, you can see all these important elements. See, there was really like a lots of luck because all these damage mechanisms are definitely, the structure is actually falling apart, and there's like a local stuff that is there, but locally, globally, structures survive, and it's really like a miracle that it has survived. And again, this is a reduced model, so you cannot have a guarantee that the bigger size model would actually survive.
Is this a real structure?
Yeah. Pardon me?
Is this a real structure?
No, this is, you can see, this is the structure. This shaking table, you cannot put the real size structure. I mean, the biggest shaking table is in Japan. I think they can put something like a 2-story building or something like that, you know. And then they constructed another shaking table at the University of California, San Diego, on the outside, where this weather is always good in California, especially in the south. I forgot now what they can put, but they cannot put like really high-rise buildings. So in Italy, they have these small shaking tables. And this, you can see that, I mean, this hall is definitely too small to have people living there, unless really like a small prison for somebody if you want to. This is probably, it looks to me something like a 2 meters by 2 meters, you know, not more than that, you know. Because you can see how many bricks are there. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, let's say 30 bricks. And bricks are typically, remember, these are not the strange, like French bricks, these are smaller bricks. So they are like, say, 20 centimeters, so maybe, or 10, 15 centimeters, so this is roughly like 3 meters or 4 meters, not more than that. So definitely it's not the real structure. And you can see this structure survived by some kind of big miracle.
But what was the intention to do this test? Because also it's not a real measuring because it's not doesn't have that concrete around.
The tension, it has concrete. up there on top is the concrete. Yeah, this is really why they all stay together. This really helped. This here on top is the concrete layer, cerclage. It's called, okay. So this really gives us the stiffness on top of it. And of course, the built-in condition gives us the stiffness. But being able to model this, it's really very complicated. So it is really the idea first. So this one you cannot do the real life testing because on the shaking table you cannot put unlimited weight. You put only the weight you can afford, which you can then move to simulate the earthquake. So you have real earthquake simulation, but you don't have the real size of the structure. So you really get into the problems of how to estimate the real size of the structure. And this is kind of the problem that one has to worry about. So how to get, when you get estimate on something very small, how to get really the true, let's say, behavior to something very big. And this is a serious problem. I wanted actually to give you also like some very recent work in which we try to do that. First of all, how this could be done, okay? If you don't have any question on this one, let me stop this one. And I can also try this one. Let's see. Okay, this will be the idea. Okay, so this will be fine, right? So let me try to share another movie. So one possibility you'll get a real size structure would be this one. Basically, you have a. Let me go here and stop it here. So, for example, this was done in the European research center called ELSA. In fact, this is Ispra. It's a small village in Italy, very close to the border of Switzerland. And then Europe decided to take really lots of money and put some special installation there. So among other things, there is this special installation which can do real-life testing of the structures. And instead of shaking table, there's something called reaction wall. In other words, what you can do, instead of simulating the earthquake by moving the basis of the structure, like I show you for this masonry structure, here what they do is they can get the real-life structure, like this one, selected here, is a typical villa, is a typical house of rich people in Greece. Typically have like a two-story building with the nice balconies and maybe not symmetric because it's supposed to look beautiful. And then you fix the structure, you bring real-life structure, that means you really construct the way it is constructed in Greece, and instead of simulating, instead of running earthquake, because it now becomes too heavy, you cannot put on any shaking table which is available, now you start pushing the floors of the structure in the way that is supposed to be doing earthquake. So here I show you this movie, you can see that you keep pushing this against the reaction wall, so the structure starts shaking like real earthquake, and you can see these little ants are going very quickly. In reality, this movie has been, we speed it up, we put a very fast motion, so it looks like earthquake. Otherwise, in reality, the way they do these tests, they kind of predict acceleration of the earthquake, then they go to the equation and they compute what would be the corresponding displacement. Then they move the structure with this displacement at the level of floors, and then they get reaction from moving from these hydraulic jacks. And then they take this reaction, they go back to the equation, they compute what is now acceleration for the new step, and then they move it over and over again. And sometimes this is combined with the lunch break, with the coffee break, or whatever, cappuccino in Italy and stuff like that. So the idea is like these people go in the normal speed, nobody's running around, but you record, you say that the behavior is not rate dependent, and you simply let it go and basically then combine these results, and you have something that looks like a behavior of the real structure. So you have like a full-size model understanding this damage mechanism for a particular structure. But unfortunately, again, this cannot be done for each and every structure. This reaction wall has to be huge. So up to now, we can do something like a 2 or 3 story building, and that's about it. So these are kind of things that have to be done. So more typical result is really this one, where the structure is too small, like this. Like this type of thing where I showed you already, where basically the structure is too small, so that you cannot really, when you establish the damage on a very small size specimen, the question is whether now this is going to work in a very large size specimen. So in fact, you take that this structure is a composite material. Basically, the masonry is a one way. It's a clay. Then you have these joints, which is mortar. Then you have these concrete, what do you call it, slabs, which are supposed to strengthen the structure and so on and so forth. So basically, the idea is here that the question really becomes, what can I do in order to get a guarantee that this will be possible to do for any type of size of the structure. So basically, let me then try to give you how this is going to be possible. So up, right, up. Okay, and then let me try to find this one. There's something called size effect. In other words, when we establish the behavior of the material on the very small size specimen, then what we want to do like a larger size of specimen. So basically, that was the idea that I wanted to show you in this way. So in fact, this is really recent work. It's so recent fact that I have presented it in the conference of World Congress that is currently taking place on computational mechanics. This congress was supposed to happen in July 2020 in Paris, and they had probably 4,000 participants because computational mechanics is a very active area. And at the end, what happened that COVID came and everything became completely perturbed. So again, this congress is a virtual congress. I actually brought some of my students to make it bigger, but still half of the people decided not to participate. And we now have a virtual congress taking place every afternoon. So those who are not registered, registration will not give money, but still you have to pay money, you cannot see this. But I can only show this one through my Zoom session. So if I now take it through my Zoom session, let me see if it works. That was the idea that I had to show you this. So I can do this presentation. I can just keep quiet and not talk because this guy is talking anyway, and it's the same guy I just recorded previously. So here it is. All right, and then I make it bigger. Okay, do you see the screen? Everything is fine?
Yes.
Did you confirm?
Yes, we can see.
Perfect. And then I run the show. Okay. So we listen together what this guy has to say.
Professor, can you increase the volume, please? In your computer.
I already have maximum volume.
The volume is not.
Is it better?
Yes, it's better.
This is we have carried out in collaboration with the team at TU Braunschweig of Herman Matisse, and also with the colleagues at the University of Sarajevo, my former doctoral students, Henrik Kraljevic and so on. Basically, here's the outline. After brief introduction and motivation, I would like to present the multi-scale computational method, the way we use it. And then what's really characteristic is the ability to incorporate microstructure probability distribution, which then, of course, has a benefit for giving you a more comprehensive description of microstructure details, but it has a drawback of being much more computationally demanding. Hence, we have to switch to the reduced order modeling at the macro scale. And what would be, I would say, original point is the ability to develop reduced order modeling with the macro scale, which is a finite element invariance community that can provide a very detailed description of the full set of 3D failure modes over a concrete material, something like that.